So this is from a textbook by Cooper and Storer. It's a really nice textbook, but it summarises for us perfectly what it is we're getting at in terms of this data set. So during incremental exercise, minute ventilation, VE, increases ever more rapidly towards its maximum, VE max, and you will have seen that in previous exercise tests that you have run. However, throughout lower and moderate intensity exercise, VE is coupled to the VCO2. At higher intensities, a point exists when VE becomes dissociated from VCO2, and it is this that is termed the ventilatory threshold or gas exchange threshold, or you may even see it referred to as the metabolic threshold. I think the metabolic threshold is a bit of an outdated term, but you may see it referred to that as well. So let's think about what that is. We are really concerned with the VE response. So VE is minute ventilation. Minute ventilation is a function of breathing frequency and tidal volume. And so we know that as we go through incremental exercise, quite clearly there has to be an increase in minute ventilation in order to bring in the atmospheric air, which is rich in oxygen, and also to help expel the carbon dioxide. Now, at lower intensities, what is fascinating is that how closely the minute ventilation couples or is connected to the VCO2. So we stumble here on a really important point, that the driving mechanism for VE is not a lack of CO2, or it is not the QO2. It's not the QO2 at the muscle. What is the driving mechanism is the QCO2 at the muscle. So in other words, the amount of carbon dioxide that is being produced is directly affecting the minute ventilation. Remember that CO2 is actually an inhibitor to cellular function, and CO2 binds to red blood cells, and the affinity of red blood cells to take up CO2 is really powerful, and particularly when we produce high amounts of this. So the key thing to recognise is that what drives minute ventilation is the CO2. So if you aren't producing an awful lot of CO2, as you would expect under low intensity conditions, then you have a low VE. However, what we start to observe is that as we move through a range of intensities, there is a point where VE becomes disassociated from CO2. They drift away, and that drifting away represents this point where the amount of CO2 we're producing is in excess of the minute ventilation. It's not that minute ventilation has reached its max, it's purely that the minute ventilation cannot meet the QCO2 response in the muscle. So the net result is that we get a dissociation between those two key parameters, and that is the ventilatory threshold, gas exchange threshold. And if you think about that, that sounds very similar to what we've referred to in previous podcasts in terms of the blood lactate response. Remember, we referred to in the blood lactate data about the blood lactate concentration representing the balance between appearance and disappearance of lactate, and that at submaximal exercise intensities there was a matching between appearance and disappearance, and then when we got to the turn point we suddenly found that there was a dissociation, that there was more appearing than could disappear. And now all you have to do is backtrack a little bit more and think about the association between lactate and CO2, and suddenly it becomes all tied together. And we'll explain that in more detail as we go through the mechanisms of ventilatory control. So this is from a review paper from Holman, which was published in Sports Medicine in 2001. But the reason for showing you this is, if you look at the data sets that you can see, we can see conventional responses, so we can see the lactate curve, which again, if you look at that lactate data, it's pretty hard to identify a lactate turn point off that curve. But we can also see, for example, if we look at heart rate is just linear against exercise intensity, same with the VO2 response. We can also start to see, though, that there are quite significant responses for a key parameter which is referred to as the VEVO2, which we will look at later, and also in terms of minute ventilation itself, if you look at the minute ventilation curve, it shows that curvilinear response, which looks a bit like the lactate curve. So if the statement from Cooper and Storer is correct, and biologically it is absolutely correct, then what we should be looking for is a point where we get a dissociation between VE and VCO2, because that represents the point where we are producing more carbon dioxide than we can actually eliminate. Well, why would that be happening? Well, at submaximal exercise intensities, the predominant energy pathway is aerobic, so we're producing our CO2 through the tricarboxylic acid cycle. But as the exercise intensity increases and the QO2 at the muscle increases, and the net result is an increase in QCO2, we start to rely more on anaerobic substrate metabolism. In other words, we now start to increase CO2 production. Remember, glycolysis works about 18 times faster than the TCA cycle in terms of the generation of ATP. So in other words, we're producing CO2 at a faster rate. So quite clearly, there is going to be a point when we transition from predominantly aerobic to predominantly anaerobic, where the CO2 production exceeds the minute ventilation, and must represent that point where we have that threshold, or as we've looked at in the lactate data, the lactate turn point. So it's a really neat idea of providing us a non-invasive estimation, which is particularly useful if, for example, you've got participants who don't like providing blood samples, or can't provide blood samples, or in laboratories where it's not convenient to take blood samples. So it's a really useful indication, and particularly because it is non-invasive, and that there is a good biological connection between the lactate response, or appear to be between the lactate response and the ventilatory response. So here we've got some data. This is from a review paper from Wasserman. I've added the red line on, but what you can see here is we've plotted VE versus VCO2. So VE in litres per minute, and VCO2 also in litres per minute. So remember what VE is. VE is the function of breathing frequency and tidal volumes. That's the volume per breath. Submaximally, and we know it's submaximally because we look at the VCO2. Remember what we said, the VCO2 increases linearly initially. Submaximally, you can see that there is a linear relationship between VE and VCO2. But at around about 2.5 litres, notice now that you get a disproportionate increase in CO2 to VE. Can you see that it starts to bend away from the trend line that I've put on? And that is because of what we're going to refer to in a moment, of a second source of carbon dioxide. The fact that we've transitioned from predominantly aerobic to predominantly anaerobic metabolism. So we're producing more CO2 than we can take in air. So it's a disproportionate rise. Yes, breathing frequency will increase. Yes, tidal volume will increase. But they cannot increase in a proportional rate to the CO2 that is being produced.